Hello everyone. Today I want to answer a big question that has been on your guys' minds for a long time. So, the question that has probably been on your mind is, why is flux useful? And the answer behind that is that flux is actually used in a lot of physical situations. And before I get into that, I just want to quickly review the definition of flux. So, in math, the definition of flux is described as the integral, the double integral of a vector field dotted with the surface vectors over its surface. So we can express this as f dot the normal vector over the area. Note that in this case, originally our area had an orientation. So this is our vector with a normal orientation. But in this case, I just removed the vector from the area and moved the normal vector inside of the expression. So we're taking the dot product of the force vector or whatever field vector is with the normal vector little n. So what does flux look like? Well, I'm going to draw a sphere here. So this is our sphere. And we're going to have field vectors that point through the sphere. So here are little field arrows pointing out. Now, let me draw a few shingles over here. These are your shingles of area dA. So this is your field vector pointing along this sphere. Now, this is your field vector, but we also need to take in consideration the normal vector over the sphere. So, in this case, here's our normal vector, little n. Notice how the normal vector changes direction because the sphere is curved. And so, in some cases, the normal vector and the force field vector will have a certain angle between them. And that means we cannot just multiply their lengths together as if they were always in the same direction. Instead, we must take the dot product. So, f dot n, using the dot product, is equal to the length of f, or the magnitude of f, in this case, times the magnitude of n, times the cosine of the angle between them. So what it looks like is, here's our f vector, and here's our normal vector n. We are trying to find out the length of f that basically falls onto this normal vector. And so we're only taking in consideration this part of the field vector that falls onto n. Now, since I've already kind of reviewed what flux is, let me start by giving some physical examples. So, the first example is, in elementary school, you've learned that if you have a positive and a negative charge, they will attract each other. But if you have a positive charge with a positive charge and you put them close together, they're going to repel in opposite directions. Same thing will happen if you have two negative charges. Now, the problem you're probably going to ask yourself is, well, okay, I can see that happening, but how do we depict it? So, the way how we depict it is by creating a vector field around each charge. So, for a positive charge, we're going to draw arrows that point away from it. So the field lines are pointing away from the positive charge right here. And if we have a negative charge, the arrows are going to point into the charge, like this. So, if we put them close together, they're going to start to attract each other. What's going to happen is we can draw these little dotted lines of the vectors pointing from the positive charge that go into the negative charge, just like this. But if we have two positive charges, then they're going to repel, and so the arrows will behave differently. As you can see here, the arrows are going to bend away from each other along this dotted line. Same thing will happen with negative charges, by the way. And now, since I've talked about attraction, repulsion of charges, as well as their vector field lines, I can start to talk about flux. Let me make this charge somewhat bigger. So, this is our same positive charge. And let's say we draw these arrows pointing away from the charge, like this. Now, let's say we create an imaginary surface around the charge. Or in this case, it could be a real surface. So, let's say we create a sphere. Alright, so here's our charge and here's our sphere. Now, what's going to happen is, in physics, we define the electric flux as the flux of the positive charge through this sphere. So, pretend that here's our little dA again. So here's our little area. Here's our normal vector pointing outward. And again, here's our normal vector pointing outward. And so, when I draw these little normal vectors pointing outward in all directions, what's going to happen is, if you look at the directions of the normal vectors, they're in the same direction as the flow away from the positive charge. And so, because they're pointing in the same direction and not in opposite directions, the flux of the field, let's say the field dot, the normal vector, is actually going to be greater than 0. And so, when we take the surface integral and sum up all the dot products through this expression right here, because all of these individual components are positive, the whole expression, so the whole integral over the surface area of this entire sphere, will also turn out to be positive. And so, if you have a positive charge, you will have a positive flux. Let me just write it quickly down here. So a positive charge, just to rephrase, generates a positive flux. Alright, that sounds cool, you say. But what about negative charges? Well, for a negative charge, you're going to generate a negative flux. Let me draw it again. So, if you have a negative charge, let's say we have our negative charge right here. Just like this. Alright, let's draw a little black sphere again. And here's our little dAs over this charge. So, here's our normal vector pointing out. just like the previous example. And we note that unlike the first case, in this case, because the charge is negative, the field vectors are pointing into the charge. And as they're pointing into the charge, the blue vector and the normal vector are pointing in opposite directions. That means the angle between them is 180 degrees, and so the cosine turns into -1. So f dot n here in this case is less than 0. And because it's less than 0, when you take the surface integral of it, it's actually going to be less than 0. So now, in this case, for our negative charge, we will generate a negative flux. Is everything making sense so far? All right, good. Then I'm going to talk about another example here. So you're probably thinking to yourself, okay, well, this makes sense qualitatively, but what about quantitatively? We know that flux gives us a certain number. So we're not just concerned about the plus or the minus sign, but we are also concerned about the actual number of the flux integral. Well, flux tells us the rate of flow over a given surface. But what does that mean exactly? Let's say I change this charge from not a +1 charge, but to a +2 charge. So, if this is +2, let me double the number of arrows here. By doubling the number of arrows, we're actually increasing the density of the field vectors. And so we are basically saying, all right, this charge +2 is stronger than a +1 charge. Therefore, we're going to double the number of arrows to symbolize the strength of this charge. So let's draw another set of arrows right here, like this. Now, if you notice here, these arrows are also going to point in the same direction as the normal vector, similar to before. And so, what's going to happen is we're going to double the flux. We're going to double the flux because we double the charge inside. By doubling the flux, we're doubling the rate of flow over this given sphere. The same thing will happen to the negative charge if we change this from a -1 charge to a -2 charge. And now, let's take a step away from electricity and let's move to magnetism. So, magnets behave slightly differently than electrical charges. Just as a quick note here, in these two cases, the electrical charges aren't moving. So they're not moving in a wire. They're just stationary and they're sitting there. So, let me move on to magnets. This whiteboard's kind of dirty. I think it's the eraser. All right, let's draw a magnet right here. Here's our North Pole, and here is our South Pole. Now, what do magnets look like? Magnets, if you draw the field lines, are not going to behave in the same way as electrical charges. Instead, what they're going to do is they're going to flow out of the North Pole and back into the South Pole. like this. They're going to point outward, and they're going to point back into the South Pole. Now, this is what a magnet looks like. So unlike a magnet, unlike electrical charges, they don't start at one point by themselves or sink into one point. Rather, they're always going to point back toward themselves. This is actually a pretty cool fact, but if you try to cut a magnet in half, what's going to happen is you're going to end up with a North Pole and a South Pole and another North Pole with another South Pole. That means these two magnets have their own little quote-unquote circulation over here. Just like this. That means you can never find a magnet with a North Pole by itself or a magnet with a South Pole by itself. Physicists haven't found whether a North Pole is possible, whether it is possible to isolate a North Pole by itself yet. So if you do, just let me know. I'll be very interested. So why are we talking about magnets? Well, in the previous case, we have talked about electrical charges and their electrical flux. But when we talked about flux, it was always in terms of just a number. That means the flux is not changing over time. In the next example, I'm going to give an example where the flux will change over time. And here's how it will look like. In middle or high school, you have seen this. When you move a magnet into a coil of wire, let's say the coil of wire is like this. Here's our little volt or a current meter over here. Now, as we leave the magnet here without motion, the meter's not going to do anything. But if, let's say, we move the magnet into the coil of wire, the needle's going to twitch this way. So it's going to twitch to the right. But what's going to happen is, if, let's say, we pull the magnet out, the needle is going to twitch this way. So it's going to twitch to the left. And this leaves us wondering, okay, we see that it qualitatively has this behavior, but how do we really describe it? Well, for those of you who are curious, there's something called Faraday's law. So, what Faraday's law states is that when you have a magnet when you have a moving magnet, what often happens is you can generate a changing magnetic flux. I'm just going to denote the flux as phi of the magnet over here, so I'll call it B. And what it's basically trying to say is, this is your voltage difference. E is your difference of voltages. So, if, let's say, you're moving the magnet into the coil of wire, the phi of B expression here is going to change. And so, when it changes and you take the derivative of that, you generate a voltage. Notice that if, let's say, you move the magnet into the coil of wire, the needle will twitch momentarily. But if you leave the magnet in the coil of wire without any movement, the needle is going to move back to its original neutral position. That is because if you move it inside, but you leave it stationary, there's no more change, and so the derivative is 0. I'm going to draw a few diagrams, and hopefully it will clear this up. So, I'm going to erase this and I'm going to draw just one coil of wire here. One coil of wire behaves the same as many coils of wire, but I'm just going to make it easier for us to see. So, here's our magnet. Here's our loop of wire. And what we're going to do is we're going to move the magnet toward the coil of wire. So, what's going to happen is we know that the magnet has flux, has vector field lines. So, they're going to point outward like this. So, as the field lines point outward, here's how we can actually interpret this. Instead of viewing it as just a coil of wire in empty space, let's view this as a disk of area instead. So, here's our disk of area, and here's our magnet. Let's call this 1 second, 2 seconds, and 3 seconds. So, let's say for the first second, we start moving the magnet in, but very slowly. So, what's going to happen is, if we look at the magnetic field lines, before they curve outward toward the center, they still move rather straight. So, I'm going to draw the magnetic field lines only pointed slightly bent. And we're going to define our normal vector pointing away from the magnet. So in this case, here's our normal vector. Now, this is for 1 second of time. So we have some positive flux going through this. In the next second, as we move the magnet closer to the coil of wire, the flux is going to increase even more. So let me draw this through more arrows. And here is our normal vectors n, again, pointing away from this disk of area over here. Now, if you look at this, we have more flux through this loop of wire. In the third case here, as the magnet continues to move, there will be even more flux. So again, we can draw even more arrows through this. Alright, once that's done, what is actually going on? When you move a magnet through this loop of wire, what's going to happen is, you know how in the previous example we saw the needle twitch? Well, what's actually going on is this generates an electrical field. But unlike the previous case where all the electrical fields were pointing away from the charge, in this case, they're going to move in either a clockwise or a counterclockwise pattern. So it's going to rotate like this. If we move the magnet in, the field is going to rotate this way. If we pull the magnet out, the field is going to rotate this way. That means the minus sign here was actually just meant to correct the direction of the rotation. So in physics experiments, they have proven that if you move the magnet in, the current will flow this way. And so to correct that, they just added the minus sign to make sure that the rotation isn't this way when the magnet moves in, but rather in a counterclockwise pattern. All right, so we've seen how the electric field moves. So as the electric field moves this way, it's going to push the electrons in the wire, since the wire is conducting, in the same direction as well. So in this case, we've seen that in the 1 second, 2 second, and 3 second cases here, the flux is increasing. So this is increasing. That means the derivative of this is also a positive number, because the derivative will be increasing. So the derivative, because the rate of the change of the flux is increasing, that means the derivative will be positive. And so all right, this is increasing. Now, we added the minus sign here just to make sure that the current doesn't rotate this way in a clockwise pattern. It's going to rotate counterclockwise. Now, let's do the case. Let's give an example of the case where the flux isn't increasing over time, but it's actually going to be decreasing over time instead. So let's reverse the scenario here. Let's say this is our loop of wire again. In 1 second, you're going to have a lot of magnetic field lines pointing out. So let's say, in this case, the magnet is already positioned halfway through the coil of wire. And in this case, we're pulling it back out. Here's our normal vector. And these are our little disks of little areas over the disk. Now, we have a very strong rate of flow in the beginning. As we start to pull the magnet out, the field lines are going to get less and less dense. Notice how, in this case, the field lines are positioned farther away in this area of the magnet compared to this area. So, in the 2 second example, the number of field lines passing through this disk will decrease. So, compared to the previous case where we had 5 arrows, now we have 3 arrows left. And the same thing will go for the 3rd second case. So, instead of having the magnetic flux increasing over time, now it's going to decrease. As this is decreasing over time, the derivative will also be negative. So the derivative of this will be a negative number. Negative, but in this case, remember that we had a negative sign over here. That means if we have a negative and a negative number, it's going to be a positive number. That means when you pull the magnet out, the current is going to start to rotate this way instead. It's going to rotate in the clockwise pattern. And so your current will flow the other way. This, just as a quick recap, this is meant to be an example of changing flux over time. In the first two examples, I gave the example of static flux. So the situation was very static, and we found the flux, but it was just a number. In this case, the flux is a function because it is changing over your time. And we can see how flux can be used to describe a number of physical situations here. I hope this video was helpful in making flux intuitive, and make sure to let me know any questions that you might have or any mistakes in the video. Alright, good luck guys.